Assalamualaikum. My name is Saputeri binti Saifuddin from Group 3, Section 5, DAC 22502, Structural Design, and we will present our group project. Our group consists of 5 members. Let me introduce the team members. Start with me, Saputeri, as the project leader, Nur Anis Suraya as the structural design leader, DIAN AJLIA as load analysis leader. Next, Nur AIZAD as tech pro coordinator, and lastly, AIZATUL UMAIRAH as documentation and reporting specialist.
First of all, I would like to start with the introduction. The structural design of a single-story residential house in Pago, Johor focus on designing key components such as beams, columns, and slabs to ensure structural stability. This project links theoretical knowledge with real-world application through manual calculation and step pro modeling. All designs follow Eurocode standard in terms of loads, material strength, and safety. Overall, the project develops technical skills and engineering judgment from design to final reporting. So next, I will continue with our objective. Our objective is to compare between manual calculation and step pro and provide reasonable justification for any discrepancies. Second, to ensure structural design follows proper engineering standards, especially Eurocode, including in terms of loads, types of materials, and size of structural parts. And last, to design a complete structural layout for a single-story residential house located in Pago, Johor, taking into account safety requirements and structural functionality.
Assalamualaikum, my name is AIZATUL and I will explain about architectural layout. Firstly, the building measures 6 meters and 7.5 meters. It's giving a total built-up area of 45 square meters. Next, the central 1000 mm wide opening serves as a corridor or passageway that facilitates smooth access between rooms and has internal circulation and may also allow natural ventilation and light to flow through the building. Secondly, the layout demonstrates a functional division of space, where each room is clearly defined with specific dimension, making it suitable for various uses such as living, working, storage, or utility areas depending on the intended purpose of the structure. And lastly, for the overall, the design reflects compact yet highly efficient space arrangement. It's maximizing the use of the available floor area while maintaining clarity, order, and flexibility in interior planning.
This is our structural layout. It shows the arrangement of beams, columns, slabs, and walls based on the architecture plan, compiled with area code, design standard, ensure structural stability and transfer used for analysis, detailing, and construction.
So first we need to calculate the beam calculation. Beam calculation need to calculate for all span. So for this one, we calculate the loading and analysis for span A/122. So the first one, we need to know the surface of beam. We got 2.19 kilonewton per meter. Characteristic of permanent action GK 9.03 kilonewton per meter. Characteristic of variable action QK 1.44 kilonewton per meter. Design action W, we got 14.35 kN per meter. Then we also need to know the shear design VED by using formula WL/2, we got 17 kN. Moment design MED by using formula WL²/8, we got 10 kN meter. Then you can see M bulk is 466.6 kN meter, is larger than MED 10 kN meter. So it is singly. So we need to know the neutral axis depth x by using formula M equals to 0.454 FCKBX times width D 0.4x. Then we insert the data. We got dx is 112 mm or 8 mm. So we use dx 8 mm. So we need to check the maximum depth by using formula x over d. So we insert the data 8 mm over 447 mm. Then we got 0.02 is smaller than 0.45. Then we need also to know the level arm Z by using formula Z equals to D over 0.4x. Then we got 443.8 mm. Next, we need to determine the area AS by using formula AS equals to M over 0.87 FYKZ. Then we insert the data. We got the AS request is 52 mm square. Then we look at the table. The provided is 2H25. The AS provided is 982 mm square. Then we need to know the shear reinforcement by using formula ASW over S equals to VED over 0.78 FIK d cot theta. We insert the data, then we got 0.039. Then we try the link H6 and the SSW is 56.6 mm square. Then we calculate the spacing by using formula ASW over with the shear reinforcement. Then we got 1451 mm. Then we continue with maximum spacing as max by using formula 0.75D. Then we got 335 mm. Then we continue with to calculate the deflection. So for the percentage of required tension reinforcement, we use the formula P equals to AS request times hundreds over BD. Then we got 0.047. Then we need to calculate the reference reinforcement ratio. Then we got 0.005. So from that, you know that P is larger than PO. So we use this formula, which is L over D equals to K 11 plus 1.5 square root FCK PO over P minus P prime plus 1 over 12 square root FCK square root P prime over P. Then we insert all the data. Then we got 11.80. So next we continue with the modification factor for steel are provided. So we need to know the AS provided over AS request. Then we got 18.9 is larger than 1.5. So in the next calculation, we need to use the 1.5. So next is the allowable span effective depth ratio, L over D. So we need to times 11.80 times 1 times 8.5. Then we got 17.70. Next, we continue with the actual span effective depth ratio. We got 2,400 over 447. Then we got 5.37. So the actual is lower than the allowable. So it means that is okay.
And then we need to find the slab calculation. We taking a slab F as one as example. We need to know the Ly per Lx is two slab or one slab. And then we need to consider the 1 meter width and design action. Then also estimate the thickness considering deflection control H. Our H is equal to 120. And then we need to find our C min, which is we got 5 mm, and C norm in 20 mm. After using a C norm 20 mm, we need to find the shear force VAD equal to WL per 2. The value that we got is 11.21 kilonewton. And then having a bending moment in two way, in short span and long span. Our short span is getting a 3.6 kilonewton and our long span is 3.31. Also, we are going to having a design of main reinforcement. Effective depth dx equal to 95 mm and effective depth dy equal to 85 mm. Our short span m bar equal to 0.167 FCKBD square, which is the m bar we got is 38 kilonewton meter. It is larger than the m. Our m which is 3.6 kilonewton meter. So we use 3.6 kNm in our AS. So the AS requirement is 92 mm per square per m. Our profile is H10 per 300 as provided is 262 mm square per meter. Our long span M bar is 30 kilonewton meter, which is larger than 3.31 kilonewton. So we use 3.31 times 10 power of 6 per 0.87 times 500 times 0.595 times 85. So our AS requirement is 84.2 mm square per m. Our new provided is H10 over 300, as prov is 232 square per meter. And then we need to calculate the minimum and maximum. Our AS minimum is 143 square per meter, and our maximum AS is 5.8 square per meter. The provide has 10 per 300. AS proof is 232 square per meter. Our verified shear force VED equal to 11.21 kilonewton. Design shear resistance K equal to 2 because it's larger than 2.45. Our P1 equal to AS proof per BD. The value that we got is 0.003, which is smaller than 0.02, so it is fine to use. I will calculate VRT C using a 0.12 kilonewton K times 100 P1 FCK power of 1 per 3 BD. So the VRD that we got is 4.6 kilonewton. Then we need to calculate the Vmin using 0.035 K power of 2 per 3 FCK power of 1 per 2 BD. The Vmin that we got is 47, which is we use VED equal to 11.21 kilonewton. And then we need to get a new P that we got is 0.001 and PO equal to 0.005. Our P prime equal to 0. So our L per D equal to 176.5. The modification factor for span steel area provided equal to AS proof per AS requirement. The value that we got is 2.585, which is larger than 1.5. Use 1.5. Allowable span effective depth ratio is L per D equal to 264.75. The actual span effective depth ratio equal to L per D, which equal to 25.2.6, which is smaller than 264 that we can use. Our H equal to 120 The main bar we got is S max per slab equal to 360, which is smaller than 400 So it's fine to use. Then our secondary bar we got S max equal to 3.5 times 120. Then the value that we got is 420. And it is smaller than 450. So it's okay to use. That's all from me. Thank you.
Next, we calculate the column calculation. So the first one is uni-axial column. Uni-axial column is a reinforced concrete column that carries axial load and bends in only one direction due to moment acting about a single axis. For example, is the column B/4. So first, we need to determine the VED for each beams by using formula WL over 2. So the first beam we got 29.07 kilonewton. The second one we got 35.33 kilonewton. And the third one we got 14.13 kilonewton. Then we total up all the VED. Then we got 79.16 kilonewton. Then we need to continue to determine whether the column is slender or not. So we need to know the clay height and also the condition. So for the condition, we got condition 1, which is 0.75, and the clay height we got is 2950. So then we need to calculate the LO over B, and also limiting LO over B. Then for LO, we need to times 0.75 with 2950, then we got 2213. Then for LO over B, we got 8.85. And for limiting LO over B, we using formula 6.19 square root BHFCK over NED. Then we insert the data. We got 6.19 square root 250 times 500 times 25 over 79.16 times 10 exponent 3. Then we got 38.89. So from that, you can see that LO over B is smaller than limiting LO over B. Then we know that the column is not slender. Then we need to know the nominal eccentricity. We calculate h over 30, we got 17. Then LO over 400, we got 6. Then 20 mm. We adopt the E and convert it to meter, we got 0.02 meter. Then we need to calculate the MED for each beam by using WL square over 8. And for the first beam, we got 15.59 kilonewton meter, and the second one 22.08 kilonewton meter, and the third one 3.53 kilonewton meter. Then we need to know also additional bending moment NE by times 79.16 with 0.02, we got 1.58 kilonewton meter. Then we total up all the MED that we got before and also add the 1.58 kilonewton meter. Then we got 42.78. Then we also need to know the dimension. Then we got 50.5. Then we also need to know the D over H. We got 0.10. Then we calculate the M over BH square FCK. Insert the data. We got 42.78 times 10 exponent 6 over 250 times 500 square times 25. We got 0.03. Then we calculate the N over BH FCK. Insert the data, we got 79.16 times 10 exponent 3 over 250 times 500 times 25, we got also 0.03. So, from the chart, we get to know that ASFYK over BHFCK, we got 0.04. Then we calculate the AS. We insert the data, 0.04 times 250 times 500 times 25 over 500, we got 250 mm square. So, next we need to calculate the longitudinal reinforcement should not less than 0.12 n over fyk. So, we insert the data, we got 18.99 mm square. Then, we need to know the 0.002 bh. Then, we got 250 mm square. So, from that, we look at the table and the provide is 4H10 and the AS provided is 714 mm square.
Next is AJLIA column calculation. An AJLIA column is a straight column that carries weight from the top directly down through its center. For example, this C/4 column. First, we need to calculate the VED for each beam using formula WL over 2. Then, we got the VED for each beam, which are 65.21, 44.85, and 30.90. We total up the VED and finally we got 190.42, and then we need to know whether the column is slender or not. To determine it, we need to know the clear height and condition of our column. It turns out that the clear height is 2950 and our condition is condition 1, which is 0.75. And then we calculate the LO using formula LO is equal to the condition, which is 0.75 times the height 2950, and we got the LO is 2213. Next, we calculate the LO over B, which we got 8.85, and the limiting LO over B using formula 6.19 square root BH FCK over NED. We insert the data, 6.19 square root 200 times 500 times 25 over 190.42 exponent 3, resulting to 22.43. So, from here we can see that the LO over B is lower than limiting LO over B. Hence, the column is not slender. Next step is calculate the N over BH FCK, which the N is 190.42 exponent 3 and the B is 2250, H is 500 and FCK is 25, which we got 0.06. From table 3, longitudinal reinforcement in brace rectangular columns with Asian load, we got the AS over BH FCK is 0, resulting in the AS also 0. We also need to calculate the minimum requirement for AS, which using formula 0.12 and over FYK, and we got 45.70 millimeter square. So we provide for H12, which 452 millimeter square. Next is for biaxial column. A biaxial column is a column that carries load from the top and also bends in two directions at the same time. For example, column A/1. To calculate this column, first as the previous column, we also need to total up the VED, which we got 35.85. Next, we also need to determine whether the column is slender or not by calculate the LO over B and limiting LO over B. It turns out we got the LO over B is lower than limiting LO over B. Hence, the column is not slender. For biaxial, next step we need to calculate the MED for each beam using formula WL square over 8. For first beam, we got 11.64 and the second beam we got 10.33. Next, we need to calculate the EZ per H over EY per B, and it should be equal or more than 0.2. And also EY per B over EZ per H, and also need to be equal or more than 0.2. To calculate EZ, we use formula MZ over NED, and we got 288.15. And to calculate EY, we use formula MY over NED, and we got 324.69. Finally, we got EZ per H over EY per B is 0.44, which more than 0.2, and EY per B over EZ per H is 2.25, which also more than 0.2. Next step, we need to calculate mz over h prime and my over p prime to know which case is this column. Finally, we got mz over h prime is lower than my over p prime, which is in case 2. For case 2, we use formula m prime y is equal to my plus beta times b prime over h prime times mz. To know the beta, we need to calculate the NED over BHFCK. We got 0.01. By looking at the beta table, we need to do interpolation and we got beta is equal to 0.99. Then we insert all the data to the previous m prime y formula and we got m prime y is equal to 40.96. Last step is we need to look for the ASFYK over BHFCK from the chart. To know which chart to look, we need to calculate D2 over H, which we got 0.1. To read chart, we need to calculate the MED over BH squared FCK, which we got 0.03, and NED over BH FCK that we got 0.01. And finally, we got ASFYK over BH FCK is equal to 0.07. We calculate the AS and we got 43x millimeters squared. Lastly, we need to know the AS mean and max using formula 0.12 n over fyk and 0.002 bh for the AS mean and 0.04 bh for the AS max. AS mean we got 8.60 and 250, and AS max we got 5,000. Hence, our AS is still within range.
This is how our load look like in our stat pro. The red area mean it having really high stress, meanwhile the purple or blue having a really low stress. Our whole structure load is about 70.551 kilonewton over 1 m 1 dl. This is the difference between manual calculation and step pro. In manual calculation, we are having a 2D simplified equilibrium equation, approximate diagram, mid-span formulas, manual capacity check, approximate and conservative. In UI, in step pro, we are having a 3D frame, automatic from 3 analysis, detailed beam force and diagram, full displacement, force provided design separately, and hide include the 3D effect.
Next is the conclusion for this project. In conclusion, the structural design project successfully achieved its goal of developing a complete structural layout for a one-story residential house in Paguh, Johor in accordance with Eurocode standards. The design ensures safety, functionality, and stability by arranging beams, columns, and slabs based on the architectural plan. Load analysis involving dead and live loads was conducted, and StepPro software was used to model and verify structural performance. The project demonstrates the importance of technical accuracy, appropriate use of engineering tools, and effective role distribution. Overall, this project applied theoretical knowledge to a real-world scenario, strengthening both design understanding and professional skills. That's all from us. Thank you.